Hi everybody. Today we're going to be talking about the concept of chromatography and what it means for forensic science, how do we use it, and how can it be useful. So chromatography itself is a technique that we use in science to separate mixtures. So what that means is I have a liquid mixture. It's made of lots of different components, but I need to find a way to separate them out. When we're talking about liquid mixtures in particular, this can be really hard to do. So one of the techniques that we use for that separation is what is called chromatography. Chromatography can break these components up, all of these little pieces of a mixture, and we can analyze what's in them. We can identify what those materials are, maybe by molecular weight or something like that. We can purify them to make sure they are pure substances, and we can quantify them, meaning we can count how many there are in relation to another. So in more simplistic terms, it is a separation technique that is separating things for their affinity to a mobile phase. So we're going to see what those terms mean in a second. This slide here, so some of the different things that we use chromatography for, usually these 4 items. So what are these in a little more detail? So some terminology that you're going to have to kind of be familiar with as we go through here are going to be these 4 items here. So the first one, affinity, is, the first one is mixture, which is when you have 2 or more substances that are physically combined. So they are not chemically bonded, meaning I can separate them from one another. An example of this would be salt water, okay? So in salt water, even though everything looks exactly the same, I can't really see where the salt is or where the water is, it's all homogeneously mixed together. It is a mixture, so the salt is not chemically bonded to the actual water molecules. They're just in the same container. Affinity then is what we call an attractive force. So it is the natural attraction or force between things. So it's kind of, you can think of it almost like magnetism, like they're attracted to be next to each other. So we see this also in chromatography. Then the 2 terms that have to do with chromatography are going to be these ones here, this mobile phase and this stationary phase. So the mobile medium or the mobile phase is what's carrying the components, whereas the stationary phase is the thing that does not move at all. So it's just sitting there stagnant, and you'll see what that looks like in a second. We mentioned it on. So how do we actually use chromatography? We see that when we're trying to analyze something with chromatography, we're examining this mixture, we're examining what's in it and what their relationships are to another. When I'm trying to identify it, I'm looking to be more detailed. So I'm going to put that little note there. So this is a more detailed analysis, and it's based off of known components. So we're doing kind of comparative chemistry. Purifying is when we're trying to isolate whatever component it is, one that we're interested in. And then quantify is looking at the amount of each substance. So I can do all of these things using chromatography. So it's actually quite useful when I have an unknown mixture. So what are some different places that use chromatography? Where is it used regularly? Pharmaceuticals. If I'm trying to create a new medicine or a new drug, I want to make sure I know exactly how much is in that product before I give it to the next step of testing or allow a human to consume it. So chromatography can be really useful for quantifying how much medication is in something. Chromatography is used in hospitals to do blood and alcohol testing. Law enforcement will use chromatography to analyze some kind of sample. So let's say I find a sample of some kind of unknown liquid at a crime scene. I can do chromatography on it and identify what that sample is and what's all in it. Environmental agencies use this to test for pollutants in water supplies. Manufacturing plants will use this for purification of chemicals. Like chromatography is a very valuable and very useful application of chemistry in lots of different ways. So there's 4 major types of chromatography that we'll typically see being used. We will be using the latter 2. So we're going to be doing paper chromatography and thin layer chromatography. Not that the others aren't important, but those are just the ones that we'll be doing. So in liquid chromatography, this is going to separate liquid samples kind of by weight. So what happens is you pour over beads. They're kind of like these glass silica beads. and they separate by size. So the bigger ones sink to the bottom. Gas chromatography is similar. The only difference is you're vaporizing those samples. So this is really useful in quantifying and also for identifying. So if I have a sample where I don't know what's in it, I can use gas chromatography and figure out exactly what is in that sample. So if I find maybe something that I suspect to be drugs at a crime scene, I would use gas chromatography because it's going to be the way that I can see exactly what chemicals are in that sample. Paper chromatography and thin layer chromatography are also very helpful to us in science. So paper chromatography is separating a dried liquid sample, and it's done on a paper strip, and then a solvent runs through that paper strip. So we will be doing this with pens. So we'll be using pens and pen ink and trying to separate it into all the different pigments. Thin layer chromatography is very similar to paper chromatography. The difference is that you are putting your dried liquid sample onto what's called a silica gel plate. So this is going to be using a very thin layer of silica as opposed to paper. So a very similar concept, and you'll see what that looks like in a second. So the way chromatography, and specifically paper chromatography, works is you have a sample that is placed on a sheet of paper. So imagine like this on the side. You put your little sample here. And what happens is you stick the very bottom of that sample in water. So imagine this is in a big beaker of water here. Okay. That water will trickle up through the paper because we all know that paper is absorbent. That's why we use paper towels for things. And you can actually see the water moving through the paper towel. It is adhesive, and it wants to be soaked up into the paper towel. The paper towel has very strong what's called capillary action. So paper in paper chromatography does the same thing. That capillary action will pull the water up through the paper, and then depending on how well the solvent or how well the ink is soluble, it will dissolve into that solvent, meaning it separates the pigments. So what I end up happening is if I have a mixture of 3 different pigments that form black ink, as that water travels through the paper, that ink will separate into those 3 different pigments and actually show up on the paper as 3 distinct blobs on this paper. So it'll be actually quite colorful. So here's a traditional setup of what you would see with a chromatography setup. So for paper chromatography, you have your paper strip, and you'll notice down here at the bottom, this is all water. Notice that the water is below the ink dot. So we put the ink somewhere up here on the paper. We want the water below the ink. Otherwise, the ink will just dissolve right into the water, and that's not going to be any good. It's not going to be helpful for us at all. So we don't want that to happen. So we put the water down below the ink spot, and we literally just let nature take its course because the water is going to be pulled up through the paper, and as that happens, this ink spot is going to start to travel and maybe turn into a red blob and maybe a blue blob up here and maybe a green blob up here. And what we'll end up seeing is quite a pretty array of ink that has separated from this original black mixture. So this is what it'll kind of look like, and you'll have this for all 6 pens. So we'll be doing this for 6 pens, meaning you have 6 setups like this. So you'll literally have this set up times 6, okay? So this is essentially what it'll look like, and you can see, a little bit difficult to see here, but you can see these are 6 different types of inks that we'll be using. We are actually using these exact same ones, and you can see even though they're all black ink, they will separate out into different pigments based on the brand of ink it is. So some different examples you will see being used. We can use liquid chromatography to figure out plant pigments, so look at photosynthetic pigments. Thin layer chromatography is really helpful for chemicals and unknown substances. Gas chromatography is really, really helpful because it shows us these really distinctive peaks that will pop up in a sample, and those peaks are for different molecules that exist. And then paper chromatography is really helpful in separation of liquids, so things like ink or dye or makeup, and we'll use it pretty frequently because it's very easy and cheap to do. So what will happen over time, you can kind of see what's happening with these samples is every, 4 to 5 minutes, these samples are checked, and you'll notice that the ink is traveling higher and higher up the paper. So as time goes by, the ink travels further, and eventually we get to the point where it travels all the way to the top of our paper, which is what we want. We look at this sample here, where our liquid has traveled from the bottom all the way to the top, okay? And our pigments have traveled as well. So how do I actually measure something based on this? So let's say, if we're looking at that like this, the solvent or the water has traveled this distance from bottom to the top, okay? So this distance right here. My ink that I originally started with, so imagine this ink started as a little black dot right here, okay? Has traveled up the paper to a certain location, okay? So 2 things I need to calculate what's called RF value. So RF value is a retention rate, essentially. So it's measuring how far a substance goes in the solvent. The further it goes, the more soluble it is in that substance, and the smaller the molecule. So if we look at the distance that the solute travels versus the distance that the solvent travels, all we do is divide those 2 values. We measure from the initial spotting line, so this is the line that you draw in pencil. Your ink spot gets put there on the bottom, and then you just let the water run its course. So let's say we're looking at this example here. I have 3 substances, A, B, and C, and if I look off to the side, my entire solvent, okay, so this is my solvent, and we remember RF is the solute distance divided by the solvent distance, okay? So if I know that my solvent distance is, I'd say that's probably like 4.7. The distances that the solute then travels, so all of our little ink pigments, is going to depend based on which one we're looking at. If we're looking at A, it got to about here, so I would say that's 0.75 centimeters. For B, it got to probably 4 centimeters, and for C, I would say 1.9 centimeters. So I'm just basing this off the ruler that I have off to the left. So for substance A, it traveled 0.75 centimeters, and the solvent, which is this liquid here, traveled 4.7 centimeters. So if I divide those 2 values, I get 0.159, and that's my RF value for substance A. For substance B, I see this one traveled quite far, 4 centimeters, and again, that distance that the solvent traveled remains the same, 4.7 centimeters. So we see this is equivalent to 0.851. And my final one, which is substance C, travels 1.9 centimeters. The solvent still travels 4.7 centimeters. And here our answer is 0.404. So I find these 3 RF values. And one thing to keep in mind, the highest RF value that an RF could be is 1.0. That means the pigment traveled the same distance as the solvent. It got all the way to the top. Okay, so just jot that down. So what you need to be able to do is look at a chromatogram, just like what I have shown on this value, this image here, be able to identify a pigment, how far that pigment traveled, and then calculate its RF value based on the distance that the solvent traveled, which we see here. So please make sure you understand how to do that. If you need to rewatch this video at any point, please do so, but it's really important that this concept makes sense to you because we'll be doing a lot of these calculations.